After talking about the exponential function and their graphs, in this lecture video, I'm going to show you what is a logarithmic function and the graph. So what is a logarithmic function? It is basically the inverse function of an exponential function. So remember, for example, an exponential function graph might look something like this. So it is a one-to-one function because it actually passes the horizontal line test. Therefore, if exponential function is a one-to-one function, then we can find its inverse, and its inverse is actually called the logarithmic function. So if people ever ask you what is a log function, it is simply the inverse function of an exponential. All right. So a logarithmic function is an inverse function of an exponential function. That is, if I have an exponential function with the base b to the x power, then its inverse, which would be f inverse of x, which would be denoted as log. This is how we read it. It's a logarithm with the base b of x. Okay, this is read it as logarithm with the base b, whatever that base is, of x. So let me turn on my calculator real quick. I'm going to do some graphing here. So on the calculator, since we all using a little bit different calculator, different version of the TI calculator, on the calculator though, when you press the word log, and this is what's cool about it, right above the word log, there's a 10 to the x power. Okay, 10 to the x is referring to as exponential. So its inverse will be the log. So when I press the word log, it's automatically using base 10. So if you don't see a subscript down here, it's automatically a base 10. All right. So let me kind of do this real quick with you. So I'm gonna say 10 to the x, second log 10, base 10 to the x power. I'm gonna graph it. So this is an exponential function. Okay. It shoots up very fast because its base is actually 10. So then its inverse, that will be log of x. So remember, inverse functions are interchange between the x and y coordinates and the x and y variable. So the second graph here, this is actually the inverse of 10 to the x, which is log with the base 10 of x. Let me shrink my window down a little bit. I'm going to just go to -5 to 5. Make my picture pop up a little bit. All right, exponential 10 to the x, and this is your log. Okay. Now I'm gonna go to the table. I'm gonna go delete 10 to the x real quick. Go to the table to show you that if I actually come down here, log with a base 10 of 0. If x is 0, it's actually considered as an error. Okay, the function does not exist. You actually cannot take a log of a 0. So let me come back out here. And I didn't mention this before, doing it right now. Log of a 0 is always going to be defined. You cannot take a log of a 0. You cannot actually take a log of a negative number. Okay, it doesn't exist. All right, so I just wanted to kind of graph both of these to let you see what they are. So let's just kind of quickly look at its characteristic. I'm not so worried about the transformation right now. I just want to kind of tell you kind of a few facts about them. So your logarithmic function, okay, is always going to be a one-to-one function as well. So this picture right here is where my base is actually greater than 1, maybe like using a base 2, base 3, so on and so forth. If the base is actually between 0 and 1 or the proper fraction, then my log function picture will look this direction. All right. I have a vertical asymptote at x equal to 0. The domain is always from 0 to infinity, unless we put some, unless we actually begin to add transformation on here. But normally, domain is from 0 to infinity. I'm going to do a graph here in a minute at the end of the video, so we can write out the domain. The range, okay, this I keep on going down, this I keep on going up. So is the one with the base that is between 0 and 1. All right, you got x-intercept, you got y-intercept, and I will show you how to. I will actually show you how to find the x-intercept in a different video when we begin to solve our logarithmic equations. All right, there's no y-intercept for this particular for these two particular pictures because my domain started at 0. Okay, but using parentheses, that simply means my function never actually touches the y-axis. All right, and you got your increasing and your decreasing. All right, so let me quickly begin to introduce this. So far, log function is the inverse of exponential. Now I also introduced using base e before. So natural logarithm. If we ever change the base, okay, maybe like a 2, a 3, maybe like a half. If I change the base of a log from base b to the base e, then we actually get what we so-called the natural logarithm, which is denoted as ln. So when you see natural log of x, that is simply saying it's a log with a base e of x. Okay. So so whenever I'm using a base e for my logarithm, that is called the natural log. All right. So natural log is just the inverse. I'm going to graph it real quick. So if I use base e to the x, okay, it's an exponential function. It looks something like this. So its inverse, which is the natural log of x, the graph will look this way. All right. All right, let's do some evaluating. I'm just going to round a couple decimal place just to kind of show you how to do this. So far, we know we cannot take a log of a 0, and we cannot take a log of a negative number. Same with natural log. Cannot take a natural log of a 0. Remember, natural log is a logarithm, just using a base e. Cannot take a natural log of a 0 nor negative numbers. All right. Log of 100. So if you don't see a subscript down here, that's automatically referring to using base 10. So I'm just going to say log of 100. All right, the answer is 2. It kind of makes sense because if I convert, well, I'm actually going to show you that later in a different video. I'll actually show you how to convert logarithm. Actually trying to teach you how to figure out how you can take logarithm convert into exponential so you can actually figure out the answer. I'll do that in the next video, I think. All right, natural log of 2. All right, just a couple decimal, that will be 0.693. All right, just kind of show you how we can use natural log and logarithm to evaluate an expression. So my calculator is using base 10 for the log. So if I actually have a logarithm that does not use base 10, then this is very important. I got to use this formula called the change logarithm basis. So for any log basis a and b, and with any positive number m, so if I have a log with a base b of m, all right, so let's say, let me just kind of write it here, kind of give you an example, okay? If I have a log with a base 2 of 5, how do I key this in the calculator? Well, I actually can't do it in my calculator because every time when I press log, I'm using base 10. So using this thing called the change logarithm base, my b is 2, my m is 5. Then we can convert our logarithm base, okay, into log with the base a of m divided by log with the base a of b. So what is base a here referring to? A can either be base 10 or it can be base e. All right, so what that means is for my log base 2 of 5, my b is 2, my m is 5. I can say this is going to turn out to be log with a base 10. I'm not going to write 10 here, of my m, which is 5, divided by log with the base a, which is 10 right now, of b, and b is 2. I can put that in the calculator. Now, if I say base a is e, that's also referring to as natural log, right? Natural log is logarithm using base e. So that would be natural log of my m, which is 5, over natural log of my b, which is 2. Both of these are actually give you the same answer. And that's what's cool about it, is when I say log with the base 10 of my m divided by, this is only one term, okay? This log of 5 is only one term, so I don't need extra parentheses. Divided by log with the base 2, I get this answer. If I do natural log of 5 divided by natural log of 2, I get exactly the same answer. Okay, so we can use either base. We can either use base 10 or we can use base e. Okay, it's amazing how one of them is using base 10, one is using base e, but we actually come up with the same answer. All right, let's do some graphing real quick. So if you can recall the transformation, okay, this -1 outside of the function tell you that my graph will shift down one place. The +4 that is inside of my function tell me I will have a horizontal shift to the left 4 units. All right. So before I can even put this in the calculator, I got to use the change logarithm base. So I'm going to say, so my b is 5. My m is actually the entire x plus 4. So this is going to be log with the base 10 of my m. This is 2 term in the parentheses, so I'll put them in the parentheses still. Okay, divided by log with the base b. B is 10 right now, so that will be log with the base 10 of my b, which is 5. Right, just follow the formula. All right, then minus 1. All right, so let's put it in the calculator. So the first term is a fraction, so I'm going to start out with the parenthesis. All right, then I'm going to say log. When I press log, it gave me a parenthesis right away, so I can put my x plus 4. Close parenthesis. This is only one term right now on the numerator, divided by log of 5. Close parenthesis for the log 5, close parenthesis for my first term. Then minus 1. All right, looks something like this. Okay, so it shifted, right? Like I said, it shifted left 4, down 1. So that means my starting point here, this point that I'm starting at, so that means this point I'm starting at got to be -4, -1. All right, so if I go to my table, all right, oh, -3, -1, 2, 3, 4. Did I type in something wrong? Oh, yeah. No? Left 4, down 1. Yep. It says -3, -1. Yep, sure does. 1, 2, 3, 4. I'm not quite sure why it says negative. I don't know why it does not say -4, -1. It says -3, -1. But this picture right here is F4. Oh, I know why. Because if I will plug in -4 here, that will actually be a 0. Okay? If I plug in -4 here, that will actually be a 0. I cannot actually take or log of a 0. It's actually undefined. So this point, 1, 2, 3. So let me check this, okay? Negative 3.5. All right. At negative 3.5, something does exist. Negative 3.9, almost negative 4. I still got negative 4. I still got negative 2, negative 2.4 something. So this actually, this starting point, I know that point is negative 4, but that point is actually not defined over there. So I actually cannot have that point. I can say this point is negative 3, negative 1. So that's true. So my starting point, I'm going to have negative 4, but the y value here is actually undefined, which is true because negative 4 plus 4 will be 0. Log of a 0 is actually undefined. All right. So I actually don't really know exactly what my range is. That's why I got this picture right here. Okay. My range for these pictures is actually from negative infinity to infinity. So I believe it's true because if I was at negative 3, let me go to calc value. If I said negative 3.99, all right. If I said negative 3.99, I still have some sort of y value, negative 3.9999. Okay, I still have a y value. So as the closer I am, okay, the closer I am to negative 4, my y values keep on going to more negative. So even though here it says x equal to negative 4, but we know x cannot be equal to negative 4. So let me try one more, negative 3.999. Let me do a lot of 9. Let's see what happens. No, there's too many 9, so that's basically approaching to, that's actually become undefined in that case. All right. So even though I don't know, even though my y value does not exist when x equals negative 4, as far as the domain concerned, I can actually still using negative 4 for reference and keep on going to the right to infinity. All right. So that will be the domain for this one. Now, as far as range concerned, I don't really know exactly, because the more as I approach to negative 4, my y value keep on going downward. Okay. So not quite exactly negative 1. So this part is not showing. You remember the vertical asymptote? Remember earlier we talked about the vertical asymptote at x equal to 0? Okay, so that is for maybe like a graph that is log of x. Okay, since I'm going through a transformation here, my vertical asymptote has been shifted right here. So technically, this graph is a vertical asymptote. And kind of, this graph is actually keep on going this direction. There you go. All right. So it will never be equal to negative 4. Okay. So your range, you can still say this from negative infinity to infinity. Okay. The closer I am to x equal to negative 4, my y values keep on going downward. All right. So just a quick video on telling you what a logarithm function is and what is a natural log. So a log function is basically the inverse of an exponential. A natural log is simply a logarithm using a base e, which is denoted as natural log. Alrighty, that will conclude this lecture video. Thank you for watching.